Kalojan Iliev, Chief Executive Officer of the subsidiary of Erema Engineering Recycling, talking on Erema, technologies and services for chemical recycling material input stream preparation.
So, hello everyone. Hope you enjoyed lunch. My name is Kalojan. I represent company Erema. I am the managing director of our subsidiary in Russia and also sales manager for Erema. I'm glad to be here. I was invited to hold a presentation about chemical recycling because this is also what we offer. Erema is probably known for those who know Erema, they know Erema for mechanical recycling. We are the market leader, world leader around the world. We have more than 8,000 lines. You'll see it on the next slides. But we do have solutions also for chemical recycling because this is, of course, coming up, but there's still a long way to go. I'll jump right into the presentation. Erema has grown now to a big group. We've been dealing with, let's say, or doing what we do for almost 40 years now. And as you see here, the main company is Erema with the core, let's say, the heart, let's say, of our technology, the cutter compactor, is what you see in the animation. But we also have other companies within our group which might be of interest to you. Thanks, Clarence. Please close it. Yeah, thank you. Companies like, for instance, KeyCycle. KeyCycle offers project engineering. Can you click on it? Yeah. KeyCycle offers turnkey solutions, project engineering for steps which are ahead of us before, let's say, the extrusion part, where you need debaling, washing, shredding. They can do, let's say, the project engineering, they can do turnkey, and also maybe another company which I would like to introduce, which will be also interesting to you, is company 3S, which is our main production company. So at Erema, now we do the assembly of the machines, but the metal works, let's say the steel works, the CNC drilling, this is all done by company 3S, and they produce the core parts for the extrusion, for the filter systems, the screws, and so on. Thanks, Clarence. Okay. So Erema has grown to a large group. As you see, as I saw it before, yeah, with this business year we'll have more than 330 million, I guess, turnover, more than 900 employees. We supply around 350 extruders per year now, so on average every day. And Erema is somewhere in the world started up. And as you can see here, I know those numbers are a little bit, not up to date, and we're around now we have around 8,000 lines worldwide. And we are proud that on our machines, around 20 million tons of plastics are recycled every year. As you see here, of course, the main market is Europe, because, of course, historically they started earlier with recycling. Also, recycling there is driven by legislation, as we heard it before lunch. There are laws being passed, there are initiatives which also help the market to develop. North America, of course, is picking up, also Asia, but also in Africa, as you can see here, we've placed quite a few lines, and let alone in South Africa, we have around 130 machines. We also have subsidiaries around the world. Usually we work with dealers on all 5 continents, and subsidiaries are mostly, let's say, of course, in the main markets, China, US, Russia, Bangkok, but also in South Africa. Yeah, we started up, so my colleague from South Africa, Erema Africa, is here as well. So, what is our stance, our position, our view on chemical recycling, since I was asked to talk more about chemical recycling today? Well, as you see here, we think the chemical recycling in the medium and in long term, in the long haul, will complement mechanical recycling. It will be the one thing that will be the next step, let's say, but it will not eliminate mechanical recycling, not at all, to be honest. If you have a look at the plastic value chain, yeah, if you look at it, so the further you go back, yeah, the more energy you have to put in. So of course, the best thing would be to reuse it, of course, yeah. If you go into mechanical recycling, so you're already very close to the final product because you pelletize it and then you can use it again for new products. Solvent-based is also rather close, let's say, to that loop. And then, of course, if you go all the way, you see here, yeah, going back into to petrochemicals, then, of course, you need the most energy to be put in, and that, of course, is a matter of costs. So that is why we do think chemical recycling will complement, it will be necessary for those streams which cannot be recycled mechanically, but it will not be the ultimate ration and solve everything. Definitely not. So, and that's why we say, you see it in the right side here, so you should follow a certain hierarchy, yeah? So, of course, try to prevent or reduce plastic pollution, try to reuse as much as you can. Then go into mechanical recycling. If you have streams which are not possible to be recycled mechanically, then you can go into chemical recycling, which of course we do push and we do want to develop, because what we do want to avoid is, as you see down below, is, let's say, okay, energy recovery, but what we do want to avoid is incineration and landfill. And that's the goal for all of us, I think, yeah. So, if you have a look at, let's say, the complete life cycle of a plastic product, you would say from the product you go down to collecting, sorting. So from the product you go down to collecting, sorting. And then every process, further on, needs shredding, washing. You need to clean the material first. It doesn't matter whether you're going to mechanical recycling or chemical recycling, you need a material preparation, which is pretty much the same. From shredding, washing, where's my, oh, there we go. From shredding, washing, you go, then you can go into mechanical recycling. This is what we do most for the moment, yeah. And then you're ready again to convert it. You can go into solvent-based recycling, which would be the second stream, or, for instance, chemical depolymerization. Now, we do participate in such projects, but they're not. There's just a few of them, They're still in the, let's say, startup phase, really. Solvent-based, we have, for instance, cooperation with another Austrian company, where, let's say, we mostly concentrate on the way to prepare the material stream, let's say, to take out humidity, to flatten it out so to have no peaks. So this is without extrusion. The chemical depolymerization can include the extruding part. I mean, I have to be honest. Most of those projects, or actually all of them, are subject to NDA, so non-disclosure agreements. I'm not really, let's say, I can't tell you much about it, but still, they are out there. They are pretty, let's say, promising projects. Like if you talk about chemical depolymerization, there is this startup in France. Startup is, of course, I mean, they've been funded really well. They work together with Erema, and they have 500 million euro funds. So, and in their case, their, let's say, process requires they go into a steering tank, and what they need is actually, and this we were talking about PET now, yeah, PET to PET. What they need is a high surface. So what we do, our part is, we create from flakes fluffy pellets, you could say, yeah. So it's foamed pellets, which later on in their, let's say, in the process, due to the high surface, the reaction goes quicker. Yeah. So, but again, those are first projects, first steps. Some are very promising, but yeah, let's see what the future will tell. What I will be talking about mostly is that part here, the latter part, which is thermal conversion. I would say 80% of our projects within chemical recycling are going into pyrolysis, where you see you have the whole, you go through the whole chain. So, since you know what our, let's say, our view is and the possibilities you have, so what can Erema offer, especially now for chemical recycling? As you see here, of course, we have the first part, which is the let's say preparing the input stream, flattening out, taking out moisture and so on, to the further process, which is, let's say, in that case, pyrolysis. And this is important for every recycler, be it mechanical or let's say chemical recycler. You also need the first part here. Has to be done well. So, which is of course collecting, sorting. We were talking about this. We need more volumes, more numbers, up definitely. But we also need good shredding, good cleaning, good washing processes. They also need to take out, even chemical recyclers need to take out PVC. You don't want PVC inside, you're less than 1%. I mean, you have chlorine, you have sulfate, you have all those sins which you don't want to have later on in a petrochemical process. So they need as good as it gets, material preparation, just like mechanical recyclers do. And here we offer, let's say, we have the technologies, the Erema, let's say. I will talk about this in more detail. And then we have, again, our company, KeyCycle, who can assist and help out with turnkey, with project engineering. So they can help out with those questions like, how do you sort it, how do you shred it, how do you wash it? How to prepare it for the next step. All right, so why does it need an extruder at all for chemical recycling? I've talked to people and many are like, chemical recycling, hey, just take the waste as it is and put it in somewhere and then dissolve it and that's it. Well, unfortunately not. It's not like this. It's not that easy. You need, as I said, you need to prepare the material first. You need shredding, washing, and even that is not enough because, as you see here also, after you get, let's say, the material, be it from the truck, mostly you get it in bales, of course, But you see here, in the animation, that this stuff, after it's being washed and shredded, it's still rather fluffy, So it's you have high volumes, almost no weight. So of course, one possibility would be you put it, you feed it in directly into the reactor, cold feeding. But after all, you need some steps. You have to solve some problems. I mean, you will have some issues because you want your waste, to be oxygen free. You want it to be, let's say, you want to heat it up quickly, to make it scalable. So the problems we see here, if you do a cold feeding into the reactor directly. So first thing would be, what do you do with the fluffy waste? So you need to somehow compact it first. Then you want it oxygen free. You don't want later in your process the whole thing to blow up. So you need to take out oxygen. You could, with a lot of effort, do even that. Add some, let's say, inert some nitrogen, for instance. But then again, it's a matter of costs and effort and energy. And also, as you say here, the next step is the difficult upscaling. So if you just put in, let's say, waste as it is after the washing process, and you want to heat it up, you put in energy from the external source, let's say. You want to heat it up. And to heat it up, let's say, even up to, let's say, 200 degrees or even 300, will take up, again, a lot of time and a lot of energy. So an extruder is the best solution to heat up, to put in energy quickly, to heat up, let's say, material which is, in our case, so we take this fluffy stuff, the washed flakes, we put it in our preconditioning unit. We heat it up already at the preconditioning unit, you will see that later on also, up to almost melt temperature. And then we don't lose the energy, we push the material straight into the extruder. And from there, so the extruder works from the melt temperature up to then whatever it is, 300 degrees. And that he can do within 1 minute. So it's the best and let's say the most effective way to put in energy to melt up that material as quick as you can. Okay, we need an extruder, we got that. So why not go into the, let's say, the conventional extruders? Yeah, we can take that fluffy stuff and put it into a single screw or twin screw extruder. Well, again, so you will have again the issue with rather high volumes. So you need to somehow reduce and compact it. So what they have to do is then again agglomerate it. Another energy step, yeah, another step, additional step to prepare the material. And you lose energy because of that, because by agglomerating the material, you heat it up, again, almost maybe to melt temperature, but then you have to cool it down, or let it cool down if you want to transport it further to the extruder, because you don't want it to ignite by itself. So you heat it up, you lose energy, you have to cool it down, and then you put it into the extruder, which is again a long extruder, which from room temperature then has to heat it up all the way from 20 degrees up to 250, 260, 300, whatever the task is. Yeah. So here we see, as you see in the bottom part, here we see that the optimal solution really would be to use the preconditioning unit where we heat up the material quickly, then put it into the extruder with our countercurrent system and solve, let's say, all those problems with humidity, with, let's say, different material streams all in one step. So what does it look like? So this is the Erema. We call it the Erema principle. This is the preconditioning unit I was talking about. So you see the material coming in. You have the single screw extruder, and we transfer then the hot melt via melt pipe to the, in that case, yeah, chemical reactor, pyrolysis. It's a pyrolysis reactor, which then the melt, then or the fuels are then transported into a distillation column, where you fractionize the different the oils into different streams, which you have like let's say long-chained like fuel, naphtha in between, or waxes, which are let's say the short-chain slugs, which you would then sell to petrochemical refineries, for instance. So again, what does the main, the heart of our, let's say, line do, the cutter compactor? It's a disc with knives where the material comes in. Can be rigid material, can be flexible packaging, film material. Let's say in case of films, we reduce, so we cut the material down, we homogenize it in that case. Because of friction, there's no hot air inside, yeah? So because of friction, we heat it up, then we dry it, of course, yeah? Due to the higher temperature, it starts compacting, and we use this buffer also, we can use it to do some, let's say, to add some dosing to it. So there are, let's say, projects where you need additives, you need something to increase reaction time, and that's where you would, for instance, work with this. So this is, and the way how we feed it, is by what we call the countercurrent principle. So we feed the material against the screw direction, which means that we fill up the screw as much as we can. And that's also very important because it's a stable process, and what you see here also on the chart here, we have a much broader temperature window. Why is this important? Why is this important also for chemical recyclers? Because we can go up with the temperature within this unit, within the cutter compactor, at a higher temperature. We can work with a higher temperature, which means we almost at melt phase feed into the extruder. Why is this important again? It's a matter of where. Because coming to, in all those streams, you have a lot of abrasive materials. You have sand, you have stones, you have whatever. That causes wear on your extruder. But if you heat the material up that much that once it enters the extruder, almost immediately melts up, all those abrasive particles start floating, swimming in the melt. And that already helps you to reduce, let's say, wear. If you have a conventional system where you take the material as it is, agglomerate it, yeah, put it into, say, a twin screw extruder, you will, again, once it reaches, until it reaches melt temperature, you have a section of the screw where you have really solid, let's say, particles rubbing off at your, let's say, screw tips, your barrels, and so on. So the wear is just immense. Yeah? So this is also, again, a wear-optimized machine. So again, summing it up, this is the basic setup. Yeah? As you see, we have the preconditioning unit. So we can add whatever it is. It can be films, agglomerates, flakes. We are very flexible regarding the input material, regarding the bulk weight. We reduce moisture, yeah, from 8%. We dry it down. We have the countercurrent technology again, which is also unique on feeding, let's say, feeding the material against the screw direction and filling it up. So which brings us, like I said, higher, a broader temperature window and allows us to work with higher temperatures, which again helps off wear. And we have some other pretty neat, let's say, devices. I will go to that in my next slide. I'll show you, like the quality on polyscan and quality on and predict on wear. We have the single screw extruder, as you see, and the melt diverter. Here we help also our customers to, let's say, to define it. So if we know the viscosities, if we know how the material is composed, we can calculate the dimensions and help the customer to do his, let's say, to install the best way on how to put the melt pipe up, how long it should be, and also the melt diverter, how it should look like. So here we also have know-how. What you see here now, I just put it in the slide. This would be, let's say, the perfect solution for mechanical recycling for post-consumer, where you have filtration in the middle and degassing. For chemical recycling, we do not usually offer such machines. However, there are projects where you might need some dosing additionally, where you might need some good degassing. So also this we could offer as part of the scope of supply if it's needed. But in most cases, we have the short screw without filtration. So these are the neat devices I already mentioned. So you have, for instance, the quality on polyscan. What is it about? It's a laser, so it's a Raman spectrometry based on the Raman technology, and basically it detects within the cutter compactor your material composition. Why is this important? Again, you want to know, do you have a lot of PVC inside? Also, if you usually chemical recyclers, they say we need P, PP, maybe some PS, polystyrol. But then you detect some other things like polyamide, like PET. This is what they don't want in their process, because PET will bring in oxygen, polyamide will bring in nitrogen. And you can detect this. You can, although maybe it's not working. Let's say that it's not that accurately, maybe, because it will give you a trend. And if you have, let's say, issues at your reactor, you can look back, and check. Oh, I know why, because at that time I had some streams, some additional material streams, which I did not want to. And you can, of course, take them out via a valve. So this is another, let's say, device which can help you to reduce problems later on in the process. Also, we have predict on wear and predict on drive. So we are the first company, I guess, who introduced, let's say in our industry, who introduced predictive maintenance, let's call it, yeah. So what you see here, this ultrasound going through, and basically by sending the ultrasound and detecting how long it needs to come back, you can, let's say, make some conclusions on the wear, how good it works, how bad it works, and also you can see that on the drives, we have also special, let's say, sensors, state-of-the-art sensors, which help us to detect if something already starts to break down. Imagine if you could know that your gear is already not working, optimally, and that in that case, for instance, if you see it down here, we saw it by the vibrations. We could tell, and we saw that way before. I mean, you don't see the time scale here, but it was 6 months before the gear actually broke down. Why am I telling you this? Why is this important for also mechanical recyclers, of course, but especially for chemical recyclers who have huge amounts? You don't want standstill. You want uptime, yeah? So you can, if you see that, then you can, of course, order the gear, yeah, and have it on stock. And once it really breaks down, you can change it immediately. Yeah. So it's about, and all those, let's say, devices display. You can display this via our Blueport. This is our digital platform. And on the digital platform, you will see we have some other, let's say, applications, some apps there. You can put it on your phone. You see the machine running. You see the machine, all the values. We have like a dashboard, so you see if it's running, how much throughput you have. You see if it's working well. You see on predict on drive if you have some issues. We have maintenance videos. We have all the layouts. So every customer who buys a machine, of course, gets access to that platform. And here's an example, a typical example of, let's say, the latest projects we have. Yeah, so below you will see a typical, let's say, specification by our customers. It's PEPP. And what you see, we built extruders, single screw extruders now. We can do up to 4.5 tons, actually even 5 tons. 300 degrees, 290 bar. Yeah, I mean the pressure is not actually needed for pyrolysis. Yeah, for chemical recycling. Depends. There are some, let's say, projects who do need a high pressure. Others do not need it. However, just imagine you have a melt pipe and you have to transport the melt, let's say maybe 10, 20, 25 meters. Then you still need a pressure, you know, to transport the melt pipe. Again, twin screw extruder couldn't do that. You know, they would need a melt pipe in between, you know, to put up to increase pressure. And regarding chemical recycling, we've so far sold 24 machines, so realized already 24 projects. Most of those who are already up and running are small machines, pilot machines. I mean, we're talking about 500 kg, 800, 1000 kg. That's nothing compared to what's coming up now. So the real projects which are coming up now, I mean, the pilot projects are pretty much also based in the very same countries. We have in Japan, in Canada, UK, California, but also now really big projects coming up. Japan and Korea, which is the same technology regarding the pyrolysis. England, US. US, it's 6 machines times 3.5 tons, so that will make more than 20 tons per hour of output for that project, for instance. So the real big ones are coming up, and that's another thing which you see, chemical recycling only makes sense if you have large volumes, because then it will pay off quickly. If you have small volumes, you won't put a chemical recycling plant for 500 kilogram per hour. You won't do that, because it will simply, you know, the costs are too high of, let's say, the latter process. All right, to sum it up a little bit, so if we compare the possibilities we have, here's another slide where I just wanted to show you how we generate, let's say, and why we have such a low specific energy consumption, because again, we need a little bit to dry the material, then we heat it up, as you can see here, and then the material, the energy here is not lost because the material is fed into the extruder immediately. So the extruder starts again from 100, in that case, 110 degrees, yeah, for that material, and melts and heats it up to, let's say, to 260 or 280, 300, whatever you need. So there's no loss in energy. And if you compare again the processes with the regular, let's say this is the Erema, and this is the regular steps, which if you would say, okay, we have material, fluffy material, we dry it, we create agglomerates, and then we put them into a standard, let's say, twin screw or single screw extruder. But again, you lose energy on this. You see, you lose quite a lot of energy because the agglomerate has to cool down. You know, it can't ignite itself if you leave it like this. So you have to cool it down, and then again, you heat it up in the extruder, have all the problems with abrasive material inside, which then starts to cause high wear as well. So, and why am I showing this? We have, you know, made conclusions. We have made comparisons, and Erema, I guess, is the one company that can that has and masters both technologies. We have single screw, we have twin screw, we have this new machine concept, which was not designed for chemical recycling. Yeah, with a preconditioning unit, as you saw it, and a twin screw. Yeah, tangentially aligned. So we do have, let's say, it's like a toolbox. Yeah. So what basically the message I want to tell you is we are a one-stop shop. But we've made, of course, let's say, we made comparisons, we know what we're talking about, and we think that for chemical recycling, the single screw technology is the one that will be the technology of choice because it's more robust, it's reliable. Like I said, single screw has less issues with wear. The twin screw can also be used. For instance, we're talking about PET, and you want where homogenization or dispersion is a target, where you say you have some reactive additives, and you need to homogenize them as well as you can, as good as you can. Okay, then of course maybe a twin screw would be an option here. So, and as you can see, we have a lot of solutions which are possible and which we offer. Here's again the comparison. If you look at it, you will have it also on the presentation in the handout. But coming back to basically the beginning, if we can, we should do this. Prevent, reduce, reuse. We know that a lot of streams, of course, they cannot be reduced or reused. Okay, so we go into mechanical recycling, then chemical, what I was talking about now. But again, we want to avoid incineration and landfill. And that's the message, basically, that I want to give you. Thank you. Thank you.